Hello and welcome. I'm Mitchell Johnston and I'm here to present to you my final year project, BLE Fingerprinting for Indoor Localisation in IoT Healthcare Applications. This project stems from a larger project undertaken by Monash University called the Hand Hygiene Project. The Hand Hygiene Project is a semi-industry based project undertaken with a company called Nware. It also incorporates many faculties of the university, including the arts, IT, and the engineering department. The Hand Hygiene Project is an IoT system that tracks whether or not a doctor or nurse has washed or sanitised their hands before coming into contact with a patient. It is able to track who is in the room and will send an alert to the person if they get too close to a patient without washing their hands. No doubt that for anyone that has been to a hospital in recent times would have noticed these posters plastered all over the place reminding people to wash their hands. One of the number one causes of infections within a hospital are due to the people bringing bacteria from the outside world. This system intends to go the next step from the poster to eliminate infections altogether. There are 3 devices within the system. The BLE wearable device that passes signals to the soap dispensers, who then pass the information over to the wash station containing the gateway, where the gateway passes the information over to the cloud. However, the current system is limited in that it cannot determine whether the person is actually close to a patient, just whether they are in the room. This FYP project is designed to solve this issue by using fingerprinting to localise the whereabouts of a person in the room. Fingerprinting divides up a room into cells, creating a radio map of measured and processed signal strengths that are measured during an offline training phase. When the system goes live, it will find the location of the cell that best matches the received signal strengths observed to the ones previously recorded. This is just a quick overview for now, but we'll go into more detail throughout the rest of the video. This is an example of the fingerprinting algorithm running live. If you focus on the bottom left hand corner, you'll see that the algorithm determined the location 4, which was the correct cell number for the room setup. There's no need to work out what the other numbers mean, you'll find out soon enough. The aim of this project was to be able to at least determine 9 positions within a room with over 90% accuracy. However, the final outcome of the system only contained 6 locations and just fell short with achieving up to 87% accuracy. Now that you're familiar with the outline of this FYP and the hand hygiene project that it stems from, we'll now go into more detail about the design of the localization, tracking, in particular the fingerprinting, and how things like the wearable were designed. While we don't want to waste too much time on theory, some brief points do need to be mentioned to help shed light on some of the design choices. Indoor localization is not straightforward since there are many issues that cause varying signal strengths. These include path loss, shadowing, and multipath. Path loss does not normally have an effect on an indoor room, however, since Bluetooth Low Energy emits low power, path loss is present. The graph shows that normally path loss is a log linear relationship, however, due to the upcoming effects, the linear relationship is lost. Shadowing also has a major effect in an indoor environment. It is caused by objects blocking the line of sight of a propagating wave. Depending on the dielectric properties of an object, only some of the wave may pass through. The rest is absorbed or reflected. The biggest addition to noise is multipath, which is caused by reflected rays arriving at the receiving antenna at different time slots, making it harder for the receiving antenna to decode what the receiving packet is. When choosing what protocol to use for the wireless interaction, a list of requirements were defined. The first was that it must be as low powered as possible to support a long battery life. It then needed to have a range that could then span across the entirety of the hospital ward so that the wearable device could always be tracked, yet not go beyond that ward as other devices in other wards could also interfere. The protocol must support many channels so that it can communicate with more than one device at a time. It also finally had to have a good transmission rate so that the data can be transferred quickly. The 4 protocols that were investigated and compared were Wi-Fi, Zigbee, LoRa, and Bluetooth Low Energy. As you can see from the table, Bluetooth Low Energy was the only one that satisfied all the requirements highlighted in green. Therefore, this is why it was chosen as the protocol for this project. The hardware for this project was relatively straightforward. Each of the wearable, soap dispenser and gateway all ran off the same Bluetooth Low Energy microcontroller provided by Adafruit. As you can see up close, the Adafruit microcontroller is quite small and compact, yet has all the capabilities required of a BLE and a microcontroller. Each of the three devices could either be run off a battery, such as a lithium-ion, or an old phone charger with a USB connection. Therefore, most of the work for this project was done in the software programming on a computer. Conveniently, the Adafruit BLE microcontroller can be programmed in the Arduino IDE, using the Arduino language, which is similar to a mix of C and C++. When downloading the necessary Adafruit libraries, an extra set of example codes become available. Each of the wearable, dispenser, and gateway all use these examples as the skeleton basis of their code. The wearable device is the BLE-enabled device that the person being monitored will wear. Because of its small size, it conveniently fits within a shirt pocket. The device acts as a beacon and continuously advertises a single packet of information that contains a universal ID and the device's name, wearable shortened into 4 letters. When connected to, it uses UART to communicate. In the hand hygiene project, an actual soap dispenser contains a bracket for holding a BLE device, a battery, and sensors to detect a hand. However, in this project, only the BLE is used. However, the name is kept for consistency. The dispenser for this project can more accurately be described as an access point. The dispenser acts as a dual-role device, as it is a central device to the wearable, yet a peripheral to the gateway. The dispenser scans all Bluetooth packets it receives, looking for the wearable's name. It then records the signal strength of the packet and forwards this to the gateway. Just like the dispenser, the gateway does not actually connect to the internet in this project. The name is kept for consistency. The gateway connects to all the dispensers in the room and communicates via UART. It is this microcontroller where the fingerprinting algorithm gets performed, which then gets outputted to the connected laptop. This is a summary of the setup. 4 dispensers are separated around the room where the gateway is also present. The wearable device emits an advertising packet that is picked up by the dispenser. The dispenser then passes on the wearable's ID and RSSI to the gateway to perform the fingerprinting algorithm. For this project, 2 different methods of fingerprinting were tested. For the occurrence-based method, each cell in a room is assigned a probability distribution of RSSIs for each dispenser during the offline training phase made out of the sampled data. When in the online localization phase, the latest RSSI observed by each dispenser gets matched to each probability for each cell. The probability for a cell being chosen is the multiplication of the probability of each dispenser reading that RSSI. The cell with the highest probability will get outputted as the actual location. The second method tested was a KNN based method. Instead of storing a probability distribution, it stores the mean of the probability distribution. Now, each cell stores a mean RSSI for each dispenser. When the system goes online, each dispenser will cycle through each cell, finding the closest mean to the most recently observed RSSI. The gateway then determines what each dispenser picks as the location cell. The cell that has the most dispensers picking that location is deemed the actual location. The localization system was first developed within a small living area divided into just 3 cells. The 4 dispensers were placed in each corner of the room and the gateway in the central location. In the training phase, 1,000 samples were taken from each dispenser for each location. Printed to the serial is the dispenser number with the number of samples it's taken, the most recent RSSI from each dispenser, and the average of the last 5 RSSIs. Once each dispenser has taken 1,000 samples, the serial prints out the occurrence for both the raw RSSI and the occurrence for the average of 5 RSSI samples. The average of 5 occurrence is put straight into the gateway's code for the occurrence method and then into MATLAB to find the means for the KNN method. A test is conducted by standing in each location for 1,000 RSSI updates. Each time any RSSI is updated, the fingerprinting algorithm updates the location. At the end of the test, the serial prints out how many times each location was chosen. The accuracy is determined from the number of times the correct location was chosen from those 1,000 updates. At the start of this video, I said I would tell you what these numbers mean. So during the test, the gateway prints to the serial the latest RSSI observed by each dispenser, the average of the last 5 RSSIs, the location determined by occurrence, the location determined by each dispenser, the number of dispensers that pick each location, the maximum number of dispensers that agree on a location, and the index where it's at. And then finally, the location determined by KNN. The initial test, which just used raw RSSIs, showed some promising signs. However, it failed to be able to determine each position with at least 50% accuracy. A few methods were tried, such as the bin method and the method where more than one cell could not be jumped at a time, yet these did not provide any better results. Then, an average of 5 RSSIs were taken, and well, the results speak for themselves. Of the two methods, the KNN provided the best accuracy with over 90% accuracy for every cell. Now it was time for a bigger room. The conference room in the engineering building was big enough for up to 6 cells. Dispensers were spread in a rectangular shape and were put up against a chair to emulate being put at the end of a bed. Once again, 1,000 samples from each dispenser were taken from each cell location. The initial test provided extremely poor results. It was found that for an unknown reason, each cell was receiving different patterns of RSSIs. Cells that were getting high RSSIs previously were now getting low ones, and vice versa. Another test was conducted, but this time 3 sets of training data were taken. It was found the first set of data provided very different RSSI patterns to that of the second and third that were almost identical to each other. The cause of this is still unknown. The good sets of data were then used for another test and the average of RSSIs were bumped up to the 10 most recent instead of 5. The results were a significant improvement from the last test. Excluding cell 6, which struggled to be determined, all other cells had accuracies over 70%. While it did not reach the goal of this project, it is a good starting point for tracking people within a hospital and help prevent the spread of bacteria. So that's all for now. I hope you enjoyed the video and got a good insight into indoor localization. Thank you for watching.